Hello everyone, welcome to one more lecture of our course on heterogeneous systems, and today we continue talking about GPU programming. Now we are going to focus on the GPU memory hierarchy, the different memory spaces that threads can use when programming a GPU. We are going to go into the details very quickly, but first of all, let me very briefly recap on what we covered about GPU programming in our previous lecture. Let me remind you as well that the reference book for this course is the book Programming Massively Parallel Processors. Remember that when programming a GPU or a heterogeneous system with CPUs and GPUs, we are typically going to use CPU threads that will run on the CPU and GPU kernels. CPU threads will execute sequential or modestly parallel sections that will run on the CPU cores, while massively parallel sections of code will run on the GPU. So we will normally start the execution on the host or the CPU, running some serial code or modestly parallel code by using one single thread or just a few threads. And at some point, we will offload computation to the GPU by calling, launching, and GPU kernel. Remember that when launching a GPU kernel, we need to first define what's the execution configuration, typically the number of blocks per grid, so the total number of blocks, and the number of threads per block. When the execution on the GPU, when the kernel terminates, the control returns to the host that may execute some more serial or modestly parallel code, and eventually we may launch a different kernel or maybe the same one in iterative algorithms. Remember that our first example was the vector addition. This is the code for the host of the vector addition, where we first allocate GPU memory, then we copy data from the CPU memory to the GPU memory, then we perform computation on the GPU. We first define the execution configuration. Here is the number of threads per block, 512 in this example, and the total number of blocks, and we launch the kernel. When the execution of the kernel terminates, we copy results from the GPU memory to the CPU memory, or from the device to host, and we can finish our program by freeing or deallocating any memory array that was allocated in GPU memory. So remember, the GPU software hierarchy consists of threads at the lower level. These threads are grouped into thread blocks that are mapped onto the different GPU cores, and the total collection of thread blocks represents the grid. There is some novelty in the most recent architecture of NVIDIA, that is the H100, that was announced basically 1 year ago, and in between the thread block and the grid, the new H100 architecture defines the thread block clusters. So now, instead of having a grid composed by thread blocks, now we can have a grid composed by thread block clusters, and these thread block clusters are composed at the same time by thread blocks. So now the hierarchy is thread at the lower level, then we have thread blocks, then we have thread block clusters, and finally grid. And the interesting thing of the thread block clusters is that the thread blocks inside the thread block cluster can directly communicate with a new network that this H100 architecture will introduce. After this refresh on the GPU software hierarchy, let's go and talk about the GPU memories. Remember the floor plan of any NVIDIA GPUs, in particular this one is the H100. Remember as well that here we observe the GPU cores. Inside the GPU cores, there are different memory spaces like registers, L1, or the scratchpad memory that is called shared memory in NVIDIA terminology. These the GPU cores, or streaming processors, or SM, as they are called by NVIDIA, have access to the L2 cache And then they also have access to the external, the off-chip memory. In the H100 will be HBM3 memory. And as you can see, there will be up to 6 stacks, 3 on each side of HBM3 memory accessed by the corresponding memory controllers. But we can first check a more simplified representation of the memories in the GPU architecture. Each of these SMs or GPU cores have some control hardware, and they have the SIMD units themselves, where we are going to execute instructions from different warps. And from these small SIMD lanes, we can access registers. Each individual thread will have access to its own registers, and the access to these registers is super fast, basically 1 cycle. But threads can also access data in the L1 data cache or the nearby shared memory. The shared memory is a scratchpad memory, is a software managed cache that can be used to share data between threads belonging to the same thread block. The access to both shared memory and L1 cache takes more or less the same amount of cycles. We could say something like 5 cycles. And similar latency, we would also have to access the constant cache. This is another cache for constant data. If we go off-chip, we need to go off-chip to read from the off-chip DRAM that is called the global memory. Now the latency will be hundreds of cycles, for example, around 500 cycles. And in between the global memory and the SMs or the GPU cores, we have the L2 cache. As novelties in the H100 GPU, we will see the possibility of doing direct copy from global memory to the shared memory without having to go through the lanes in the GPU cores and the registers. And there will also be possible to communicate directly from SM to SM inside the same thread block cluster. In this H100 GPU, we'll have a pretty large L2 of about 50 megabytes, and also pretty large global memory, HBM3 memory of 80 gigabytes, and also very interesting global memory bandwidth of 3 terabytes per second that will be basically twice as high as the bandwidth of the previous generation, the A100 GPU. There are not so many details so far about this new architecture, but hopefully in later editions of this course, we will tell you more, and we will even have some experience with these different features, such as the direct copy or the SM to SM communication. But now, we know that there are different memory spaces, registers, constant cache, shared memory, L1 cache, L2 cache, global memory, and there are different ways of using them. In our program, we will use qualifiers to define where one specific value or one specific array is allocated. Automatic variables will go directly to registers. They will be allocated in registers by the compiler. And if we define inside the GPU kernel, we define an array like this, it will be a private array for each individual thread. And the compiler, if possible, will allocate it in registers as well. If not, if there are not enough the registers, maybe because this N is too high, then it will have to be allocated in the off-chip DRAM. When we want to allocate something in the shared memory, we will use this shared qualifier here. And if we want it to be in the constant memory for its access from the constant cache, we will use this constant qualifier. If we want to allocate something in global memory, we can use this device qualifier. And this device is optional when used with shared and constant. So from the point of view of a GPU thread running on a GPU core, it has access to its own registers that can use privately. Threads that belong to the same thread block can access the same data in shared memory, and threads in different thread blocks can access the same data or different data from the external of-chip memory that is called the global memory, and also from the constant memory that is allocated also in the off-chip memory, but can be cached inside each SM, as we have seen in a previous slide. So how are we going to use these different memory spaces? For now, we are going to talk about the shared memory, and we are going to see how different threads can share data allocated in this shared memory and can communicate using this shared memory. The shared memory is going to be especially useful when we have data reuse inside the same thread block. For example, if we have to apply one filter to one image and we assign one pixel of the image to each thread in the GPU, when applying the filter, what we normally do is reading pixels that surround the specific pixel that we are focused on, and we do some calculation using these nearby pixels. But one thing that you can observe here is that if this pixel is assigned to one thread and this other pixel is assigned to another thread in the same thread block, they are going to share the some values that they both will need to read. This is what we call data reuse. So these 6 pixels here will be used by both this thread operating here and this thread operating here. So this is what we call the data reuse. In the most straightforward implementation of this code, we would do just something like this. This is like the code here corresponds to a Gaussian filtering, where we are applying one filter, this Gauss here, on top of each pixel of the image, right? And these 2 for loops allow us to go over all 9 elements that are under the filter, the Gauss filter that we are applying to every pixel in the image. But as I said, here there is a lot of data reuse because these 6 elements or these 6 pixels will be used by 2 different threads. So what we can do here is take advantage of this data reuse and use one technique that is called tiling, sometimes also called blocking, that consists of defining tiles of data that are going to be reused by many different workers or many different threads. In the particular case of the GPU, what we are going to do is placing this tile into the shared memory, because the shared memory can be accessed by all the threads belonging to the same thread block. So that's what we do. We define some space in shared memory. Then we load the entire tile from the global memory, the off-chip memory, into the shared memory, and then threads will simply access the pixels that they need for their own computation for applying the filter. They will access these pixels from this array L data that is in shared memory. Observe as well that between loading the tile into shared memory and the actual computation, we need to use this sync threads instruction here, or sync threads function here, that allows us to synchronize all threads in a block. This is a way of avoiding hazards like read after write, write after read, or write after write when accessing shared memory or global memory from threads inside the same thread block. And it's important to use because thread blocks will typically have more than 32 threads. That is the number of threads that belong to the same warp, is 32. If we have 64 threads, for example, in our thread block, that means that we have 2 warps. And now remember that the execution on the GPU core pipeline is by issuing instructions from different warps. So what that means is that instructions from different warps, even if they are the same instruction, are executing at different times. So if we have 2 warps loading data from the global memory to the shared memory, we need to make sure that all the desired data is loaded, the entire tile is loaded before we start using the data in that tile. So that's why after loading, we will use these sync threads, exactly as we did in this example code here. So in order to better understand how to take advantage of data reuse, we are going to go with a very important kernel that is matrix multiplication. In matrix multiplication, what we do is performing the multiplication row by column of two matrices, A and B, and we'll obtain one output matrix C. This is our matrix C of size n by n in this simple example. This is our matrix B and A, and this is our matrix B. So when we want to compute one individual pixel, we will have to read an entire row of A and an entire column of B. The most straightforward parallelization approach is to assign one thread to each element of the output matrix C. Remember that in the GPU, these threads are grouped into thread blocks. So we are already partitioning the the output matrix C into several tiles, several parts that are assigned to different thread blocks. So all these pixels here will be computed by one thread block. Let's call it thread block 00. These pixels here will be, these outputs of element of C will be computed by the next thread block, and so on and so forth. So one thread, this specific thread here, will read this entire row, and this entire column will perform the dot product operation of these two and accumulate results finally in this output element of C. So this is the actual code. Because the matrix is a two-dimensional organization, we are using two-dimensional blocks. Remember that we talked about them in the previous lecture. So by using the block index, block dimensions, and thread indices, we can calculate the row and the column for each element of the matrix C, and then we access the entire row of A and the entire column of B in order to multiply and accumulate and obtain some final result that will be stored in the corresponding row and column of matrix C. But the observation here is that there is a lot of reuse. Why is that? Because if we have 4 threads computing these 4 elements of C here, all these 4 threads need to access all values, all elements of this specific row of matrix A. And if we think about these 4 elements and the corresponding 4 threads, all the 4 threads will have to access the same column of matrix B. So we can take advantage of this data reuse by doing a tiled matrix multiplication. In the tiled matrix multiplication, we divide the input matrices A and B into tiles, and step by step, we are going to load tiles into the shared memory and then use the data in shared memory to perform the computation faster, because accessing shared memory, as you know, is significantly faster, basically 2 orders of magnitude faster than accessing global memory. So the threads of this, the thread block that is in charge of this tile of C, will go to memory, will read the tile of A, will read the tile of B, will place them into shared memory, and then they will perform the partial matrix multiplication to obtain these values here. And then we continue repeating the same thing for the next tile, and then for the next tile, and this way we'll obtain the final results for these elements of matrix C. So this is the code of the matrix multiplication. As you can see, we first declare arrays in shared memory, and one tile of A and one tile of B will be placed there. We have these indices for row and column. We initialize the accumulator for each individual thread. And then for each of the tiles, we first have the threads go to the global memory, read the corresponding tile from A, the corresponding tile from B, and placing them into the shared memory. Then we need to synchronize, because remember, we are running likely thread blocks with multiple warps. So we need to synchronize in order to make sure that all the data of the tile is in the shared memory, and then we can compute using the tiles in shared memory, accumulating in this sum variable for each element of the output matrix. And at some point, we will write the results when we go through all the tiles. We will write the result in the final matrix. Observe as well that we need to have these sync threads also after this inner for loop, because threads will have to wait in order to make sure that all the data in the tile has been used as much as needed before replacing that data with the contents of the next tile. Okay. This is all for today. You can read more in the book, Programming Music with Parallel Processors, in chapter 5. But I would also recommend you to watch the long version of this lecture, where you can find more details about the GPU memory hierarchy, about how to perform a basic tile matrix multiplication, and also a few more details about the new H100 architecture. This is all for today. I really appreciate your attention, and I hope to see you in the next lecture.